Thanks, Jörg, for very interesting talk, and you managed to enlighten us on all three topics, which is excellent in 1 hour. That's great. Okay, so time for questions. So I think there's already a question by there are quite a few. So please unmute and ask Raja after that Vishnu. A mic problem. Okay, so Raja's question I will speak out. Jörg. So Raja is asking question. You can see in the chat box itself, but I will read it out.
Yeah, I can open the chat box.
Yeah.
Yes.
So it is how to understand jump in the Leibniz exponent jump in time. For Neumann case, is that indication of any process? Could you kindly explain?
What? The jump? Once more, please.
No, he's not able to speak. His mic is off.
Yeah.
So I think you had things were growing, no? The thing I think he's saying Leibniz exponent. Well, basically Leibniz. How do you compute Leibniz exponent? The question to me also not very clear.
Ach so. But, I understand. Okay, it's about the sketch. Yeah. Let me. I'm going out of the presentation mode. Can you still see my screen?
Yes, we can.
Okay, then let me go back, and I think I know what he means. He means this jump,
yes.
right?
Right, that's right.
Yes. Well, this is just so what you are doing is basically think of a little of the Lyapunov exponent in the 3D space along a trajectory. What happens is when you move along the trajectory and you start with perpendicular vectors, unit vectors at the beginning, then one vector gets stretched in one direction, other shrink, and they all get turned. So basically there's a tendency for them to bunch together. And this step here is basically a kind of Gram-Schmidt orthogonalization procedure, which you have to put in between to rescale everything. And that does not matter because everything is consistently corrected in the logarithm. So that's the typical algorithm, because you have to keep in mind this is separating exponentially fast. So that means you cannot keep this forever. So what you typically do is you stop, you re-orthogonalize, you rescale, and then you start again. Because what you want to monitor is the exponential separation strength. And that can be also, it's basically a relative measure, and that's why you can apply this rescaling. It's a rescaling procedure in combination with an orthogonal, with a Gram-Schmidt orthogonalization. That's an algorithmic thing. So okay. if I would have just drawn one of these arrows, it probably would not have caused confusion. Everything is very nicely documented in this textbook by Arkady Pikovsky and Politi. It's really a nice book where everything is also mathematically nicely explained and the algorithms. Yeah.
So Vishnu, you can unmute and ask your question.
So am I audible now?
Yes.
Yeah. So you have shown in the superstructures that when you add rotation, it reduces the size of superstructures, right? So I was just thinking, why not the Taylor columns which forms when we add rotation? Will they help to actually increase the size of the structures?
The Taylor columns are actually not very well visible, but the Taylor columns are here. This is full of Taylor columns, very, very small structures. And the reason is the rotation is already pretty strong here. So when you have very low Rossby numbers, you get exactly what you have in mind. But this is aspect ratio 60, so you have thousands of these Taylor columns here. And they are so small that they look here like noisy, spiky data, but this is in principle exactly the regime you have in mind. It's here.
Oh, okay. Yeah, I understood. Thank you. So I have one more question.
Yes.
Yeah. When you do the modeling, you actually take the large scale structures which transfer the energy, right?
Mm-hmm.
So I'm just thinking that whether does that assume that our energy is transferred mostly by the large scale structures and we actually ignore the small scale dynamics?
Mm-hmm.
So like are we actually ignoring the small scale dynamics which helps to transfer the energy?
In some sense, yes, you are right, and that is the models, the model which we have, the reservoir computing model, has no explicit dissipation in some sense in itself. If you would run a reduced POD model, so if you take your POD modes and you construct a Galyockian model, then this model sometimes blows up and you really have to add some additional dissipation term to drain out the energy. Okay. In the reservoir computing model, that seems not to be the case. The reason is probably because everything gets somehow distributed across this big network, and I don't know, frankly speaking, now how one can extract information about the dissipation of the small scales in that set. You probably it's probably very hard to do that, but it's a very good question. All I said is what I can answer now.
Okay,
I hope at least.
Yeah. Yeah, thank you. Thank you for the answer.
Okay, any other question from the audience?
I think Shashwat has a question, right?
Yeah.
Okay,
hello, Professor Schumacher. Thanks for the nice talk. Good talk. So, yeah, I just wanted to ask the convolutional neural network model that you did. So did you use some dedicated software, or you actually developed the code for training the model?
This is a very that's a standard algorithm. I mean, okay. The way how to set this up is, for instance, documented in this paper here. It's lecture note in computational science. And this group from the university in Freiburg in Germany has applied it to analyze the dynamics of cells.
Okay.
But these steps are very standard steps. So if you take TensorFlow or whatever software package for machine learning, convolutions and max pooling operations are there as ready-to-go routines, and you just have to yes. Can you still hear me?
Yes. Yeah.
Okay, good. And you just have to glue them together. So that we did that on our own. Yeah.
Okay.
Erik Fonder, who did this by the time when we worked on this.
I see. And if I understand correctly, the input feature, I mean, you give the 3D superstructure, the images of superstructures as the inputs.
No, we give yeah, that's the point here. We give it 2D vertically accurate picture of the temperature into image, into the machine learning algorithm. 13.5 gigabytes.
Okay.
Yeah.
I see.
Next question.
Okay, thank you.
Okay, good. Yeah.
So I'll just ask one question related to this, then I'll go to Amitav. Here, the input is your image, output is are these defects, what is the output?
Is basically this network. And now the question is, what are you doing with this network? So you basically can set up a crude dynamics, a simple network dynamics, which tells you in which way the energy is transported across the layer. Yeah. So the black regions here are regions of enhanced convective heat transfer.
Okay.
Yeah. I mean, there's certainly a contribution from the background, and we have looked at this, and we have also looked at this with respect to Rayleigh number dependencies. So we have analyzed a few of these data records in this respect. And the idea was just to come up with a simple, almost discrete network type transport model for heat across such a convection layer. It's a kind of crude model for mesoscale convection phenomena, I would call it. And it might be interesting for some as a kind of parameterization for global circulation models, if you think, for instance, about the atmosphere. Yeah. And we are actually currently collaborating with a colleague in Barcelona who is interested to apply these kind of techniques also in atmospheric boundary layers. So dry convection with flux-driven convection.
Okay, Amitabh, please go ahead, unmute and ask a question.
Yeah, I'm audible, I hope.
Yes.
Yeah, a very nice talk. Is Amitabh Bhattacharya from IIT Delhi. So I was just wondering, actually, what you just now said, it's related to that only. That I was wondering that for moist convection, have you tried to use any machine learning techniques for modeling parameters like entrainment rate or the onset of convection, like so those kind of things? Have you tried to directly model? Because those would be, like you said, more better for like GCM type of applications.
It's a very not so well understood.
Yeah.
And we are now actually getting back to this subject and studying the entrainment processes, and perhaps there are some new opportunities to also include machine learning aspects into this field. But we haven't done so far. All we did so far is just to reproduce some statistical quantities in our moist convection model, and it's a very simple moist convection model. So we don't have rain there. It's so the water content is conserved, etc., etc. Yeah.
Okay, thanks.
I guess this. Okay, Rodion has a question. Rodion, please go on.
Yeah.
I would like to ask about mechanism of the supergranular formation. Is it related somehow to inverse cascade, energy cascade?
That's a very good point. And as if you take a look, I mean, so what we have not done so far is a detailed spectral analysis, but when you see these spectra, you could think of it as indeed as a kind of inverse cascade process, and this analysis in the Fourier space somehow suggests that energy or variance gets accumulated at the largest scales in the system. So in that respect, yes, I would say it is something like an inverse cascade process, but probably if you have two-dimensional turbulence in mind, where everything can be properly decomposed in Fourier space into transfer terms, etc., then I say that we have not done this so far. The analysis which we are doing here has been done mostly in planes at constant height, because in the vertical direction the flow is always inhomogeneous. It makes it difficult to really go over the vertical direction. In principle, one could do it. I agree with you. It's possible to basically apply the machinery which we know from 2D turbulence, but we haven't.
I ask because from the first look, your spectrum looks like you observe large-scale energy, but now the question, does it come locally from the buoyancy force, or is it non-linear transfer? So for that, you have to plot the spectral flux, and if you observe negative spectral flux of kinetic energy, then it is done for sure. But there could be another scenario, non-local interaction between different scale. It could be more difficult. But now do you have any paper or any studies of the spectral fluxes for this problem or not at the moment?
No,
not yet. Oh, so
not
this
yet.
is really open,
Yes.
interesting.
Yes.
Okay,
yes.
Thank you.
Well, what I said, we could try to really convert our data plane by plane into the Fourier space, and then we we could basically take the equations and look at the spectral fluxes plane by plane. That is something one could do. As I said, in the vertical direction, it's a little bit more difficult because we are highly inhomogeneous there. And but yes, it's a good point, but we haven't done so far. So everything quantitatively which we have done is basically summarized on this slide, which I just have put on the screen now. But it's a very good point.
Thank you.
Okay, Abhishek, your question, please.
Yeah, thanks for a very interesting talk. I was thinking about the massive difference in this constant heat flux versus constant temperature boundary conditions. I have seen this in the dynamo simulations also. The community debates what are the appropriate boundary conditions. But I've not found a convincing reason why such a big difference occurs. So is there a physical reasoning? And the second question is that does it make a difference if you apply the boundary conditions on two boundaries or just one boundary? Like both boundaries having constant heat flux versus one boundary having constant flux versus one boundary having a fixed temperature. Does it make a difference?
Yes. So question one, where there is a fundamental difference, and that is the primary instability, the critical wave number of the primary convective instability.
Okay.
Yeah. And that is different. In one case, it's a finite. The rolls have a finite size. Yeah, it's roughly about the size of the height. The rolls are almost circular, the convection rolls, yeah, which would fill the convection layer at the onset of convection. In the constant flux case, you would basically have a pair of infinitely extended counter-rotating rolls. Yeah, whatever that might look like, but that's basically what it means to have a critical wave number of 0. So you have two rolls which are counter-rotating and which are extended infinitely. Yeah. So it sounds a bit weird, but that's basically what it means. So there's a fundamental difference in the onset of convection, and that is what we try to show. That is what the system does not forget about. Yeah.
Okay. Very interesting.
And this might be different when you add a magnetic field, and when you add rotation. We are actually currently looking at this. When you add rotation, it changes. Yeah, also the critical wave numbers. There have been studies on that. It becomes finite if you exceed a certain strength of rotation. So that is the first question. And the second question was about...
Does it make a difference if only one boundary has a certain kind of boundary condition?
Oh, yes, it does. So for instance, if you have a constant flux from the bottom and you don't have any flux going out at the same amount, the system heats up internally, right? The mean temperature would be a linear function of time,
right.
and there are people who have looked at this as well. So it certainly makes a difference, and it also affects typically it affects the transition thresholds if you have different boundary conditions at the top and at the bottom. But we have not considered this. At the moment, we are looking at the simplest configuration and keep the boundary conditions the same. There are studies underway where we actually have a flux at the bottom and no flux at the top.
Okay.
But this is only a simple 2D model at the moment, which is more related to the machine learning part in the past.
So the arguments on the stability goes back to Chandrasekhar and Fitz-Busa and their papers. So I find it a bit strange that if we go very far from the onset, even then the same stability arguments, they still apply. I don't know if you find it strange as well. or?
In some sense, effective. Well, I think in some way we tried to exactly show this with the Lyapunov vector analysis.
Yes, that's really interesting.
So the Lyapunov vector analysis, basically, what it does, it tells you, or it quantifies the linear instability locally, which flows on a turbulent patch, which is advected on a turbulent patch. Yeah. So we try to quantify instabilities in turbulence. Yeah, not instability of an equilibrium state.
Yes.
But the Lyapunov analysis somehow tries to do exactly this. And I know the arguments by Fritz Busse, and in principle, that is not wrong. I think the picture is really somehow intuitive, because what you can always do is you can always rescale your molecular diffusivities and viscosities by the turbulent ones, and then you get again it's this marginal stability boundary argument, which I think are very very interesting, and the physical picture behind that is at least I think very very nice. Yeah.
Thank you. Yeah.
I think Frank has a question.
Yes.
Okay.
Yeah.
Yes. So a very, very nice talk. Thank you. I have a question on the same line as Rodion concerning the effect of rotation. When you increase rotation, so you decrease the Rossby number, and then the flow is becoming more or less 2D.
Yes.
And in this case, I would expect to have some inverse cascade and to have large scales. Instead, you find smaller scales.
I haven't looked at this yet. It's a good point, but please give us some more time, and then we can probably say about this. The results on the rotation is really very very new. It's obtained just a few days ago, and we are just starting to get into it. So we have not looked in detail into transfer, etc. It's just the first things. But you are right. If you have if things become columnar in the vertical direction, then you basically would expect something which you have in the solar wind or wherever there is a kind of 2D turbulence in these planes, and then one could observe an inverse cascade. But we have not looked at this yet. I cannot say at the moment.
Frank, I would like to comment that even before rotation starts, it is already quite similar to two-dimensional flow, right? Because it is quite homogeneous in vertical direction. So I mean, the rotation could amplify this inverse cascade mechanism, but maybe it is not so important for this case.
Yeah, we have to see that. It's
yes,
a good point, and we take this as a very nice suggestion for our future work. That's a good point. Yeah, from both of you.
Okay, thank you very much.
Sure.
Could I ask a question? It's just a philosophical one, maybe. The machine learning part about these reservoir computing. What is the kind of utility of such a model? I mean, why? What is it good for if you do such an approach? Does it help you in from a fundamental point of view, or could it potentially help for some control problem maybe, or something like this?
Well, the point is that you get a relatively cheap model that mimics the dynamics of a complex dynamical system without solving the equation of motion explicitly. Yeah. So in our case here, we are solving those kind of iterative equations instead of the Bussinesky equations. Yeah. So that is first, that is, so it is a simple model that can be easily be implemented into as a subscale parameterization model, as a dynamic subscale parameterization model in a somewhat bigger flow context. And it's rather cheap. Once it is trained, it works in principle pretty reliable. It generates, this model here generates a statistics that agrees very well, a low order statistics, I have to say, that agrees very well with the statistics of the original data. That is, so it's a kind of reduced model as a Galyockin model for based on a POD analysis. It's a comparable one, but in the Galyockin case, as you know, one basically derives equations of motion from the original ones by projecting onto the modes. And here we don't do that. We basically have this iterative formula, which is just prescribing the time advancement of this model. So it's an even simpler, fully data-driven way to come up with a reduced order model.
But let's say if you change parameters, you have no way of saying how the model parameters would evolve from one state to another, from one parameter set to another one, if your input control parameters.
That's exactly the point with the transfer learning. This is exactly the point. That's what we are working on now. It is possible. As you know, also the other models are somewhat limited in that respect, but that's exactly what we are pushing forward now. We change parameters, and well, we first do it not very strongly, but at least we change the parameters and we see how well the model still works. So this is can we generalize the model to other parameter sets? That's exactly this point, which is here referred to as transfer learning. Otherwise, you're right. You train a model, it's highly trained for a specific problem, and that would be not so nice if it can be only applied for this specific problem and not be generalized to at least a few other parameter sets. Fully agree.
Okay, thank you.
Excellent. Sorry, Thomas, my mic was mute, so I could not invite you that time. I thought I was speaking, but I could not. Great.
Sorry for not waiting for the.
No. My mic was muted, so I was speaking, but I could not. That was a mic problem. Okay, great. So I'll ask one or two questions, Joerg. I mean, we are already like half an hour into question answers. So reservoir looks like is better than deep neural network because you need less number of nodes, or what is the advantage of reservoir compared to DNN? And which do you already have something like ready-made reservoir computing thing somebody has coded already
Yeah, we have it. There are again packages, and partly if you go through the libraries, you will find software packages which describe these reservoir computing models, and so we also develop our own stuff here. The good thing about the reservoir is, well, the first thing is you need some kind of short-term memory in your network, and a classical convolutional neural network does not have this. So if you take a standard feed-forward network which has an input layer, several hidden layers, and an output layer, it does not have an internal memory. These ones have, because there is this, at least for one time step, there is this delay here in terms of the information with how it propagates through the network. There are other architecture, the so-called long short-term memory networks, LSTM networks, which is the second big group of recurrent neural networks. And we have not applied them, but they also have a reasonable performance. What you need is a kind of recurrency. You need a short-term memory to process time series. If we are interested in dynamical information, you need this. If you are only interested in classification, as we do here, then you don't need that. Then you can use all the other networks, and they do a perfect job. Yeah, but if you want to process time series, and that's exactly what we are doing, time series of POD expansion coefficients, then you need a kind of recurrency. These are networks which are specifically designed to digest time evolution data.
I see. Great. Okay, I guess we have had a lot of interesting discussion. I'll make one more comment, then we'll quit. So this horizontal convection, where when heat from the left and cool from the right, that is also that is also supposed to be unstable, right? It's just unstable to Edward go. Of course, the critical value is 0 for that, I think.
Yes, in principle, yes. Yes.
So that seems similar to what your Neumann condition convection appears to be. There's some similarity I could see. So have a look at it. If you may have already thought about it, but I can see some similarities. Both are very unstable.
Yeah, but we have in our case, we always have a finite critical Rayleigh number.
Yeah, I know. So that's the difference. Yes.
120 or 720.
Right.
And
anyway, so we can discuss it.
It immediately goes. If you have a temperature difference from here to here, it immediately goes.
Right.
That's probably still a little bit of a difference.
Yeah, there is some difference, but some similarities, I thought so. Okay, great. So thanks a lot, Jörg, for a very interesting talk, and it led to so much discussion. I hope you enjoyed this.
Yes, I enjoyed it a lot. Thank you for having me, Mahendra.
It's
all the best.
Yeah. Okay, great.